Hi, and welcome back to the third of our biomolecules that we're going to look at, and we're going to start with simple carbohydrates. So the key things that we need to know for VCAR when thinking about exam questions for carbohydrates is that we need to be able to talk about the formation of disaccharides from monosaccharides and also the formation of complex carbohydrates. So we need to specifically concentrate on starch and cellulose, again knowing that these are condensation polymers of the monosaccharides. Okay, so far we've looked at proteins as condensation polymers of amino acids. We have looked at triglycerides, which aren't polymers but are formed by the condensation reaction between glycerol and 3 fatty acids. And now we're looking at carbohydrates, which are formed by the condensation reaction between small simple sugars known as monosaccharides into more complex carbohydrates. These condensation reactions form glycosidic links, which form an ether functional group. The storage of excess glucose in the body is done through glycogen, which is also a polymer of glucose. And then comparing glucose, fructose, sucrose, and the artificial sweeteners aspartame with reference to their structures and the energy content that they will release into the body. Okay, so looking at carbohydrates, these are long chains of saccharide molecules. Saccharide is the word that we tend to use interchangeably in chemistry for sugar. So saccharides are sugars and carbs are sugars. These are represented by the general formula CXH2OY. Okay, so our carbohydrate molecules contain only carbon, hydrogen, and oxygen. This is in contrast to our proteins, which can also contain things like nitrogen and sulfur. There are 3 main groups: monosaccharides, disaccharides, and polysaccharides. In this video, we're going to concentrate on monosaccharides and disaccharides. These are our simple sugars, 1 and 2 linked together. The monosaccharides are the simplest form of carbohydrates, and they can exist as C3, C5, or C6 sugars, so triose, pentose, and hexose. The ones that we will concentrate on firmly in VCE studies are our hexose sugars, which are glucose and galactose. Okay, and then our pentose sugar, fructose. The structure of these sugars is given in your data book. You have a selection of disaccharides as well as monosaccharides. You're given the structure for both alpha glucose and fructose in your data booklet. Monosaccharides, as we said before, have the general formula CH2ON. These are essentially mono sugars. They are 1 molecular unit, and they tend to exist as either the straight chain or ring form. These ones that we see here are in our straight chain form, and you can see that the glucose is an aldose sugar, i.e. it contains an aldehyde on carbon 1, whereas fructose here is a ketose sugar. It has a ketone on carbon 2. The rings can have 2 different geometric forms, which we call anomers, and they differ only in the spatial arrangement of the hydroxyl and the hydrogen groups on C1. Okay, this one here, and that is basically most evident when we see the ring form of them, not the straight chain. You are given the ring form in the data booklet, and most of the questions you'll be asked tend to be in regards to that. But remember, they do have 2 forms, the straight chain form and the closed ring form. So in addition to monosaccharides, in solution, these exist in equilibrium. Sometimes they open up, sometimes they close. Okay, and the position of that hydroxyl can change when we have ring open and ring closed. So, as we said before, monosaccharides in solution are in an equilibrium. They can undergo an internal reaction, okay, to close the ring. They consist of a single carbon ring structure, and we refer to these as Haworth projections, but these are them here, and these are the ones that are shown in your data booklet. And this is how they are shown. We have this ring structure here, which is in the plane, you'll notice that fructose, F for 5, is a 5-membered ring. 1, 2, 3, 4, 5. 4 of those are carbons and the oxygen. We count around the rings clockwise from the oxygen. So if this is the oxygen, then this is carbon 1, 2, 3, 4, 5, and 6. Okay, with glucose, we have again going around from the oxygen, going clockwise 1, 2, 3, 4, 5, and 6. The position of these hydroxyl groups, whether they are below like this one is or above like this one, the ring, is important. When these change, it changes them between alpha and beta glucose on this one here, or on carbon 4 can actually change it from glucose to galactose. So pay attention to whether your hydroxyls are above or below the ring when you're drawing these structures out from your data booklet. So you can see here, this is galactose here, and compared to glucose up here, it is this carbon here. The hydroxyl is now above the ring instead of below the ring. Okay, glucose here is below and below, whereas in galactose we have them opposite, trans across the ring. Okay, so and that changes the sugar that we're talking about. Of course, enzymes break down sugars in the body. Specific active sites, what sugars they are will determine whether or not the enzymes are able to break them down. It is critical to remember that enzymes are catalyzing all the reactions in our body, so be that breaking down of peptides, sugars, lipids, building up triglycerides for the storage of fats in our body, receptors. All these multiple different reactions require multiple different enzymes in our body. Okay, so we have multiple chiral centers. Okay, but the strain around the ring means that we are looking at different groups, so we have different enantiomers of the sugars. Key thing, alpha and beta glucose, you are given alpha glucose in your data booklet. So if we again go to carbon 1, the first one around from the oxygen, the hydroxyl, the first 2 hydroxyls are down in alpha glucose, it is up and then below for beta glucose. Okay, so alpha means the hydroxyl group attached to carbon 1, okay, and the CH2OH group at carbon 5 lie on opposite sides of the ring. So this one and this one are on opposite sides. For beta, this one, both are on the same side. Okay, so cis arrangement between the CH2OH and the OH on carbon 1 for beta, and trans arrangement for the CH2OH and the OH on carbon 1 for alpha. Of course, when we look at monosaccharides, we can see that they have a number of polar hydroxyl groups. This allows for hydrogen bonding at multiple points around the ring, meaning that they are highly soluble because they're able to form strong hydrogen bonds with water. The formation of disaccharides, trisaccharides, and polysaccharides, okay, so from simple into more complex carbohydrates, occurs via a condensation reaction. The condensation reaction occurs between carbon 1 and carbon 4, okay, forming a 1,4 glycosidic link, but essentially we lose the OH of one and the hydrogen of another, producing a H2O molecule, and then we form a glycosidic link where we form a new bond directly from the carbon to the oxygen and up. Okay, so there is no carbon here. Okay, they're actually just forming directly from the O to the position on the ring. Okay, so monosaccharides are the monomers or the building blocks of the carbohydrate polymer. They form the polymers by a condensation reaction producing one molecule of water, and of course they're broken down by the hydrolysis or the reverse of this. Disaccharides consist of 2 monosaccharides linked together by a condensation reaction. The linkage is known as a glycosidic link, but remember that COC, this is an ether functional group. Okay, glycosidic link, ether functional group of that COC that we talked about when we did organic chemistry. Two glucose molecules form a 1,4 glycosidic link, so the link between carbon 1 and carbon 4 of the next adjacent carbohydrate. These can be hydrolyzed back into the monosaccharides through acid hydrolysis or an enzyme catalyzed reaction. Remember, with esters, it is an acid catalyst for the formation of it and a base for the hydrolysis. So here are the important disaccharides that we need to know, and these are in your data booklet. So sucrose has glucose and fructose. Okay, if you want to draw the single monosaccharides of these, you simply break the glycosidic link, add your OH onto here and a hydrogen onto here, and you get the two monomers that we see here. Lactose is actually a disaccharide of galactose and glucose. Okay, so this is galactose and glucose. This one here is galactose and glucose. You are given the disaccharide of lactose in your data booklet. Okay, so remember glucose, make sure you identify your glucose. Generally what will happen is one will be opposite the other. You can see how this one is flipped around in order to form this 1,4 glycosidic link. Okay, so one has had to swap upside down because of the different position of the hydroxyls above and below the ring. Then maltose is glucose and glucose. Okay, so sucrose is our table sugar, found in sugarcane and things like that. Lactose is, of course, the sugar we find in milk, and maltose we find in sprouting grains. Okay, so when you talk about malted barley, we find maltose, but it's also the first breakdown product when we break down carbohydrates in the body. So when we go from starch, it's broken down into disaccharides, these maltose disaccharides in the first stage of digestion before being broken down into glucose. Okay, so as we said before, our carbohydrates are sweet. Sugars, we know, give a lot of energy. We can see here that if you look in your data booklet, you're given a energy value for our sugars, and we'll look at that more in our coming discussions on energy and food. But one of the reasons that we like to eat them is because they taste sweet. Monosaccharides and disaccharides impart a sweet taste. Polysaccharides actually don't. So this leads to dietary issues in overconsumption, particularly in our modern society. Excess energy is then stored in the body as glycogen, which is a polysaccharide, and eventually this is converted through to fat for long-term storage. One of the approaches to this is to use artificial sweeteners to replace sugar in things like foods and soft drinks. The misnomer about these is people believe that the artificial sweeteners don't actually contain as much energy as sugar, and this is not the case. The artificial sweeteners have about the same energy per gram as our monosaccharides and disaccharides. The difference, however, is that they have a much greater sweetness. So aspartame, which is the one given to you in your data booklet, is about 200 times sweeter than sucrose, and neotame, this one here, is 50 times sweeter than 50 times sweeter than aspartame. What this means is to get the same sweetness as we do for sugar, we use 1,000 times less or 200 times less than the amount of sugar to get that same sweetness. So while they have the same energy per gram, we're using a lot less, so what we use them in contains less energy overall. You'll notice these structures do not have the sugar structure. These are not saccharides, they're not carbohydrates. In fact, they are actually amino acids. Okay, this one is a dipeptide, if you have a look, and then it has an ester It's essentially a methyl ester of a dipeptide. And again, you'll see that we have this amide functionality and more similarities to a peptide than we actually have to a carbohydrate with these. So key things here, they have similar energy per gram, a similar energy content as sugars, as saccharides. They have a different structure, more similar to amino acids and peptides than those of disaccharides or monosaccharides. But we use far less of them in food, meaning that overall the food products that these are used in has less energy content in it. Okay, quick question VCAR exam. So I've put the structure up here from the data book. This is aspartame. So it says aspartame is a widely used sweetener. And then we have these 4 options here. Contains a glycosidic link. No, this is the condensation product of 2 hydroxyls, okay, which we see in disaccharides or polysaccharides. That is not the case here. Is a naturally occurring sugar? Nope. Does not have the sugar or saccharide structure. It is not a naturally occurring sugar. These are artificial compounds. Similar to that of sucrose in energy content? Yes, 2 amino groups in its chemical structure. This is an amino group. This is an amide, so that is incorrect. Okay, it just has the 1 amino group, which means C is definitely our right answer. Okay, that's it from me and our first video on carbohydrates, and I'll see you in class.